Right. All right. Let's resume today's discussion. We are going to move to the chapter 8, continuous distribution and the Poisson process. Right. So we are going to cover three topics today: uniform random variables, exponential random variables, and Poisson process. Right. So now let's get ourselves started. Right. So to begin with, we need to try to define the probability function. Probability function. Sorry. Probability function over continuous space. Right. So things get a little bit subtle here. Right. So let's start with recalling chapter 1. What we did with chapter 1, what we did with the probability function. Right. So a probability function really has a probability space omega. This is probability space, and we also need to define a sequence of events, or all possible events. Right. So what the requirement we have is that the if I look at the probability of the things falls into the any elements in the probability space, this has to be 1. And also that for any event such that we do need to have this kind of requirement, probability that this particular event happens has to be a number that's between 0 and 1. And the third one is that for any collection of events, collection B of disjoint events, we do need to have this kind of property. If I take the probability of the union of all these events, it has to be equal to the summation of the sum of the probability that each event happens, right? Right. So these are three really fundamental rules that we need in order to define a probability function. Now, let's start with trying to understand a bit of what's the subtleties we are facing here when our space is a continuous space. Say for instance, it's 0 and 1, 0 to 1. Right. So this is our space. So now it is no longer a continuous space. Right. So now let's imagine that we define a collection of k points, xk. Let's say that p1, p2, p3, and all the way down to pk. Right. So now let's say these are the k points, right? So this is p1, this is p2, and all the way down pk. Right. So now let's try to see what's going to happen here. Right. So let's say we want to compute the probability of x belongs to S of k. Right. So then basically it's really just that the summation of equal to 1 to k probability that x equal to pi. Right. Right. So and let's start with like the simplest the sum of the most natural distribution. Like let's assume that we want to define a uniform distribution. Uniform distribution in the sense that each point is equally likely to be picked up, and let's say that this probability is p. Now then we can sort of see that this whole probability is really just k times p. And by using the rule over here, right? So the union of events is the sum of the events. And then this little thing also at the same time has to be less than equal to 1, right? We actually get this k times p less than equal to 1. And here the subtlety is that now we haven't specified the value of k, right? K can actually be arbitrarily large. So when k is arbitrarily large, you really just says that p is equal to 1 over k, and then if we say that we let k goes to infinite, and this third property actually is still going to hold, right? So even like this collection is infinite collection, so long as it's enumeratable, the whole equation is going to hold, right? So the only way we can define p is actually 0. Right. So that start to get ourselves into some funny things that we get into the conclusion probability x equal to pi is actually 0, right? So with probability 0, right, our x is going to hit on a specific point, right? So this actually gets a bit funny, right? So because it's probability 0 on one hand, but on the other hand that it's not that it's impossible to happen, right? So the subtleties, like if you want to handle this kind of subtleties in a rigorous way, like you really need to use some sort of measure theory, measure theoretical tools to define the whole things rigorously. But for now, for our purpose, our distribution, like the whole point of here is that our distribution, when we define the uniform distribution, it's the probability of the events. The events are over the intervals. Right. So in order to address, like really circumvent this issue or not really touch this issue in this course, we really only just says that a probability that x belongs to a certain interval, right? Let's say a, it's equals to defined by something. Right. A would just like become it's really just an interval. Interval that's subinterval that's between 0 and 1, right? So we can talk about that the probability that the x falls into a particular region. We can talk about this probability, and when a probability x it hits a particular point, this point here it's always 0, right? This kind of things behaves a little bit funny, right? It takes a bit of time to digest, but if you work on this area long enough, this is actually a natural definition. But for now, we really just focus on the setting where we can define that the probability that's over an interval, right? So now we can talk about the probability distribution of a random variable, right? So let's move to the definition of the random variable. Right. We say that the probability distribution of random variable, let me just write down the most important sentence here. The probability distribution of a random variable x is given by the distribution function fx such that fx is really just that equal to probability of x less than equal to x, right? So we are still talking about the interval, right? The interval is really just that you look at the set of real points, right? So here we drop the assumption, implicitly drop the assumption that it's the probability space is between 0 and 1. The probability space can in general be anything that's along the real, right? So now this function is really defining that, like if it's fx, it's really just that there's an x here. What's the probability of that the random variable falls into this region, right? So now if we want to talk about the probability of a random variable that's belong to a certain interval, we can also easily just really write that down as fb minus fa. Right. So pictorially, it's also very straightforward, right? So there's a B point here and there's an A point here, right? So FB basically is really just that it's the probability that X falls into this interval, and FA is the probability that X falls into the blue interval, right? If I take the difference, what we are getting is this particular interval. It's really just that literally just what we want to get. The probability X belongs to A and B. Right, so this is really just the f here is also called it's as we said, it's called the distribution function, right? So by now actually it gets back to the territory you feel familiar with when you were dealing with the first probability class, right? So here really what we were talking about just now is really just that you need to be a bit careful in defining the events. Some of the events, the probability that some of the events happens, it actually becomes funny. It's 0, but it's not impossible to happen, right? Right. So after the distribution function, we can also talk about the density function. Right, so if exists a fx such that for any a that's in the real number along the real number, fa equal to integration of negative to negative infinite to a, or integration over the little f of x, then we call fx is density function of a. F A, right. So basically, right? So basically, the density function is really just that. When you look at this function, like let's look at the function f here, right? So function f is really just the function f. Here, recall that if we want to draw the function f, like at the end, it will eventually be one, right? And it has to be monotonic, right? So it has fa. If let a goes to infinite, this has to be one, right? This really just reflects that to the probability x less than infinity has to be one, right? And fa has to be greater than fb if a greater than b. It's obviously right. So probability that this is coming from the fact that probability x less than equal to a is has to be larger than probability x less than equal to b if a is larger than b, right? So this is all has to be monotonic. That's the reason we draw things like here, right? So this is the distribution function, right? The density function basically is really just that this little thing, right? So if this is the if this little region is x, right? The density function is basically the little thing purple area that's this the pink area that's describing the bar here, right? So that's the reason that when we integrate, when we do the integration, right? So we are really just putting up all the pink area together, and then we will get the area, the entire area, right? So in other words, like if the derivative of fx is well defined, then we do have the fx equal to f derivative of x. Right. So that's the density function, right? So now we can talk about a number of things, right? So a number of examples, right? So example one. Right, so just to get yourself familiar with the notion of the density function, right? So probability of a less than equal to x less than b is really just the integration of a to b density function of ax b, right? So that's basically pretty obvious, right? So why is that? So this is, as we said, is equal to fb minus fa, right? So this is by definition is the density function. We can write that in terms of the density function, integrate from negative infinity to b fx dx minus negative infinity to a fx dx, right? So now this the integration, the function we integrate is the same, so the minus is really just that we take the difference of in terms of the intervals, right? So this is a to b a fx dx, right? So this is the first example, and the second example is that we can talk about the moment expectation and e of x. It's really just that we can really just emulate what we did over the discrete cases. It's really just some integration of everything x fx dx, right? So you can, so in the let's compare that to the discrete case. All right, so in the discrete case, it's ex equal to sum of everything equal to negative infinite to infinite I p probability x equal to I, right? So right, that was the definition of discrete case, right? So you can sort of see that we substitute the summation by the integration, substitute by this value by the I here, right? So it's intuitively expressing a specific value, and this is the probability that specific value happens. The probability that specific value happens, right? So these two terms matches up. Right, so basically the moral is really just that you can really, a lot of definition just can be intuitively translated to the continuous setting, right? So the third example we are giving is the obviously it's the we want to compute the moment, right? So e of xi is really just the negative infinite xi f x dx, right? So sometimes, right, when I write things up here, it's not very obvious, right? So because my writing is not good, but when we want to define the random variable, it's a capital letter, and when we talk about the integrations here, those are the lower cases. Right. Sorry for that. Right. So these are really just obvious things, right? So let's also let's do a surf force example, right? So for any function g, right? So if we want to compute the expectation of gx, right? So unsurprisingly, it's integration of everything, the value we are interested in, and the fx and then dx. So this is this is what we are how we are generalizing the notion, the original the definitions for all these different basic building blocks in the discrete case to the continuous case, right? So now we can talk about the variance. Example 5, variance of x. It's really just the variance of x equal to expectation of x minus ex and the square. And it's really just that if I want to write down the definition, it's really just negative infinite to infinite x minus ex square fx dx. And then you can also check that this is if you do the math a little bit, right? So it's going to be the ex square minus x squared, right? It's exactly the same as the same as the discrete case. Right. So let's also try to do a bit of deviation in case you don't believe that, right? So what's the integration of this whole thing? Square fx dx, right? So let's expand this term. It's really just a negative infinite x squared minus xex, and let me just try to write down more carefully, right? So this is the capital X, this is the little x, this is the little x, right? So x squared minus x e to the x minus e x x plus e square x. So this is a bigger x, right? So times f of x dx, right? And then I can really just expand this term out, this times this, just really just pull this, expand the entire thing. It's the standard expansion, right? So what we are going to get is negative to infinite x squared fx dx, right? So these are the terms over here, right? Minus, right? So negative infinite x expectation of big X fx dx, right? And the minus, right? This would be the second term, negative infinite expectation of big X little x fx dx, right? Plus expectation of x squared. This is also a big one, right? So notice that this one is actually a constant, right? So expectation of a certain random variable must be a constant, right? So whereas we are integrating on this little x, right? So this can actually be pulled out, right? On the other hand, let's also look at this term here, right? So this is actually the definition of ex squared, right? And this term, and look at this term, right? So this is really just the e of x negative infinite x fx dx, right? So this is actually also the definition of x, e of x, right? So this term then becomes e square x as well. And then you can also see for the same reason, this is the e of square of x, right? So at the end of the day, we have the first term is e of x square minus e square x minus e square x plus e squared z x, right? So that's the reason that there are some cancellations going on here, and then we come up with that's the same thing, exactly the same thing as we did for the discrete case, right? So next, let's also continue to do a bit of a generalization, right? So recall that right, if x, so in the discrete case, right, so if there's a random variable x that's always positive, then we do have this expression, expectation of x equal to sum of I greater than 0, probability of x greater than equal to I, right? That's what we did a few weeks ago, right? That's the discrete case. Now let's generalize that in the continuous case, and this is the lemma 8.1. Let x be a continuous random variable such that x is always greater than 0, then so we can sort of guess that the continuous case, right? So if we want to mimic that, it's the summation becomes integration, and the probability is really just becomes it's still the probability, right? This is what we are guessing. This is the big X, this is the little x. We are integrating over the x, right? So that's exactly what the lemma is giving us, right? Integrate 0 to infinite probability of x greater than equal to x dx, right? Right, and you can also see that if we look at we do the proof here, and we are not going to repeat the proof for the discrete case, but you can also see that it's really just that we more or less just substitute the summation by the integration. We are already able to prove that using this exactly the same sort of techniques, right? So let fx be the density function of x. Then we have, right, so integrate x equal to 0 to infinite probability of big X greater than equal to little x dx equal to integrate x equal to 0 to infinite integrate y equal to x to infinite fy dy dx, right? So what am I doing here is that I substitute this term to here, right? So using the fact that the probability of x belong to two interval is really just the integrate between these two interval fx dx, right? But I'm integrating, there's an integration of here, right? So I just want to change the variable, so now it's not dx, it's really becomes dy, right? So you can sort of see that it's just really just a notation issue. Whatever you're integrating here, it's so long as the function is the same, it's the same thing, right? So that's the reason that when we want this to be greater than x, so this part a becomes x, b becomes to infinite. This is x, this is infinite, right? Right. So now it's what we were doing is we try to switch these two integrations, right? So right. So let me just write this down again. X equal to 0 to infinite, y equal to x equal to infinite, fy dy dx, right? So in the discrete case, we really want to switch this, right? So we sort of want to do the integration and then switch this to as well, and then fy, and then I want to dx first, and dy. Right? How do I switch that, right? So so now let's draw this plot, right? So x can go to 0 to infinite, and let's also look at y. Y can only be larger than x, right? So these are the area we are integrating, right? This is the area of x equal to 0 to infinite, and then y equal to x to infinite, right? So now when we want to switch, right, so we want to switch, we start with y equal to 0 to infinite, right? And x, when I fix an y here, let's assume that's the x can only be as large as from 0 to y, right? So x really can only be x 0 to y. This is how we are expressing the same area, so, by running over y first and then running over x, right? So this is going to 0 to infinite and 0 to y, and dy dx dy, right? Right. Does that make sense to you, right? So so now let me just write this down again. 0 to infinite, 0 to y, fy dx dy, right? So let me look at this term here. I'm integrating with respect to x, whereas this function here is a function of y, so it's a constant with respect to x, right? So this can be pulled out actually, right? So that becomes 0 to infinite fy integrate with 0 to y dx dy, right? So this part, right? So you can also write a little one here. Right, so when we do the integration, it's actually y here, right? So fy and then 0 to infinite dx dy. Oh, so that's sorry. I already did the dx already, right? This is dy. Right. So this is actually really just the definition of the ex, right? So because if you look at that, it's really just integral of that fx x dx. So what's the difference between this term over here and the term over here? it's really just that we do a change of variable name. Right. So where did we use the fact that the x has to be greater than 0, right? So we do have to use this condition, right? The reason we have to use this condition is that if x is not greater than 0, then the way we are switching the index is not going to work, right? So we care only about this little region, right? So in case the region goes beyond here, then actually this kind of switching trick doesn't work anymore. Right. So this is just another example showing to you that the discrete case and the continuous case really just have if you know the discrete case a lot of time, that you can really just generalize that a lot of results in the discrete case to continuous case in the natural way. Right. So now let's move to the next part, the joint distribution. And conditional distribution. Right. The joint distribution is really just that. Let me just write down the definition, right? So the joint distribution of x, y is really just defined as a two-variate bivariate function, right? Which is ratio. Unsurprisingly, it's really just that x less than x and y less than equal to y, right? So, and then we can also talk about the density function, right? So it's the variable x and y have density function little f if fxy equal to integration of negative to y, integration negative infinite to x, f uv du dv. Right. So again, like we just change the variable. We would ordinarily just write the x and y, but because the integration is also x and y, so we just want to make sure that we don't confuse ourselves. Right. So because of that, right, so we can also write in case it's usually true that fxy is really just the second derivative of x partial y fxy. Right. So after the joint distribution, the next thing we want to talk about is the independence. Right? So it's again that it's more or less very close to how we did in Markov chain, a lot of definition that's showing up, but here it's less heavy than the Markov chain part, right? So because we saw a lot of things in the continuous in the discrete case, right? So we just want to generalize all those things in the discrete continuous case, right? The random variable x and y are independent if for any x and y, probability of x less than equal to x and the y less than equal to y equal to probability of x less than equal to x and probability of y less than equal to y, right? So you can sort of see that this is f of x and y, right? So let's call this is the joint the distribution function of x and y, joint distribution of x and y. And this is really just the fx, x, and fy, y. Right, let me just again draw these things carefully, right? So that really just means that if we have a way to decompose the distribution function into two parts, then the corresponding random variables are independent. And similarly, we can also see that f. Right, so if I talk about the density function, x and y, it's again we can be decomposed into the density function of the two variables. And if this is decomposable, then basically we can see that the two random variables are independent. Right. So let me give you another example. Right, so f, x, and y equal to 1 minus e minus alpha x minus e to the negative beta y plus e to the minus alpha x plus beta y, right? So this would be an example of the density function, right? So so this is the density function. Let's call the joint we're talking about the joint density function of x and y. Let's assume that it's in this functional form. We are going to show that it's going to be independent. So we are going to need, we will show that x and y are independent. Sometimes when you say you say two random variables are independent, you use this symbol here. Right. So let's start with f of x, right? So this is really just that probability of x less than equal to x, right? So you can sort of verify that this is actually, you integrate everything, right? So well, it's you can sort of see that x and y and dy, right? So you integrate across the second coordinate. Sometimes you can also really just write that this is x and positive infinite, right? So this is really just that it's literally the same, right? So because this is the same as the probability of x less than x and the y less than equal to positive infinite, right? So if I substitute these two numbers into this quantity here, we get the 1 minus 1 negative alpha a x, right? Similarly, if I do fy x, we will get 1 minus e to the negative beta y, right? So now if I take the product of fx and fy y, and then you can sort of see that it's 1 minus e to the alpha x, 1 minus e to the negative beta y. You can exactly see that these two quantities are the same, right? So in other words, we sort of managed to decompose this joint distribution into two distribution functions, and that actually gives us that x and y's are independent, right? So we can actually do the same thing for f, right? So we can sort of at the density function level. Right, so I would also like the textbook didn't give you the calculation details, but I will also not give the calculation details here, right? So if we just do the this is really just that you do the partial derivative of x and xy and then xy, so you will get something like the 8 alpha times beta times e to the negative alpha x plus beta y, right? So now you can also verify that fx is alpha e to the negative alpha x and fy is equal to beta e to the negative beta y, right? So when you take the product of these two, again we get the joint distribution over here, right? So now let's move to the conditional distribution. Right. So if we have some random variables, looks like that the conditional distribution is really just that if there are two events, let's just recall that E and F are two events, right? So then probability of E given F is defined. Let's really just be careful that this is really just the way how we define that as the probability of F, probability of E and F happen at the same time. Right. So now we can talk about, so if we look at the conditional probability, let's say probability of related to random variables x and y. If we talk about the things like if I want to compute probability x less than equal to 3, condition on y less than equal to 6, that's actually pretty well defined. It's probability y less than equal to 6 and probability of x equal to 3 and y less than equal to 6, right? So if I use the distribution function is fy of 6 and fxy and 3 and 6, right? So this is actually well defined. But what happens if you want to compute the probability of x less than equal to 3 condition on y equal to 4, right? So now we are hitting the problem that the probability of the certain events is 0 in this, because of we are facing a funny continuous probability space. Let me just write down everything and then explain that to you, right? So if I want to follow the definition, I'm forced to define in this way, right? This is our attempt to make the definition, right? So probability of x less than equal to 3 and y equal to 4, and probability of y equal to 4, right? Just notice that the numerator here is actually 0. Right, so just again, like using our discussion at very early on, right, over here, right. Oh, sorry if I make you feel dizzy, right? So very early on, right? So we were talking about that if there are a set of points, and then I want to make sure that all these three conditions for the probability function to hold, I'm forced to define that the probability a random variable equals to a particular point has to be 0, right? So our denominator is actually 0 here. We have the 0 denominator problem here, and then we sort of need to find a way to fix that. Right, so how do we fix that? So how do we fix this problem? So again, we really just want to emulate the concept we use for defining the limits and the calculus, right? So we sort of want to define that as less than equal to 3, y equal to 4. Like if we really just give a little margin over here and then let the margin goes to infinite, right? So what's the probability of y that's belong to 4 and 4 plus delta, and the probability of x less than equal to 3 and the y belong to 4 plus delta, right? So hopefully, because of this margin scheme things going on, you can really just lead us to using the density function instead of the distribution function to define this term, right? So in fact, we can exactly like if you can sort of if you have the intuition, you can sort of guess that this would be the right definition: x and probability of x less than equal to x and condition on y less than equal to y. So changing that into general x and y, and this is f of u and u and y and f y dy, right? So why is that, right? If you look at this one, right, so it's really just the if I look at the limit of delta equal to infinite goes to 0 instead, sorry, probability of y belongs to y plus delta. This is exactly our definition, right? So of course that we sort of maybe is 2 times the delta, right? So there's a little delta here, right? It's exactly our definition of f of y dy, right? So this is sort of the intuition we're getting here, right? So we actually will informally tell you that why this definition is actually reasonable, right? So let's really just do the calculation a little bit. Again, like this is not exactly a very formal treatment, but the idea is to really let you see that like just using the whatever calculus knowledge you have, usually you shouldn't have too much trouble in handling the definitional issues in the continuous probability space. X less than equal to x and y has to be y and y plus delta, right? So this is what we want to calculate, right? So let me just really just use the definition delta used to infinite, right? So it's probability of y. Again, let me just write down in a different way. So those are really just the same way, right? Sometimes I feel more comfortable to write things in this way instead of this way, but they are really the same, right? So let's talk about the conditional. Let's really just directly use the definition of the conditional probability: x less than equal to x and y belong to this little interval y plus delta, right? So this is the definition, right? And Now let's really just use the distribution function fy and y plus delta minus fy y, and this is also the fx y plus delta minus fx y. Right. So this is really just the definition of the these are the really just the definition of using of the distribution function to express all these probability terms. Right. So now let's also write this down a little bit further. Delta goes to infinite mu. Let me just write down everything and then start to explain that, right? So fy y plus delta minus fy y, and then the denominator are all the same, right? So what I'm going to do is here do a derivative here, fu and fu y plus delta and partial x, and the minus derivative of fu and y and partial x and du.